Hi, everyone. Like you just heard, I'm Nathan Thorne. This is Sam Christensen and Adrian Potok, and we're going to talk to you about dead downwind faster than the wind travel. All right, so for a little introduction, we'll talk about wind-powered vehicles. Sailboats, in order to travel quickly against the wind, need to tack, which is sailing at an angle to the wind. So it's usually, if you're using a sailboat, if you're going straight downwind, you can't go fast. Andrew Bauer wrote a paper talking about possibilities of being able to build a vehicle that could go straight downwind, but actually travel faster than. So this was in 1969. But more recently, Rick Cavallaro created a vehicle called Blackbird, which he claimed that could travel dead downwind faster than the wind. So popular videos circulated by Derek Muller, you might know him as his channel name Veritasium, seem to show this behavior. But the explanations offered by Muller don't necessarily hold up with conservation of energy, so something doesn't add up. All right, so the goals of our project, we are seeking to explain this scientifically in a scientifically rigorous manner. We want to come to a conclusion that is supported by test data, exhibits energy conservation, and is in line with our existing knowledge of aerodynamics. So we wanted to construct a vehicle that was easily modifiable and could use tests with different propellers of different diameters. And we want to develop tests that are simple and easily repeatable. So here's our Gantt chart, a timeline of what we wanted to do with this project. So the project scope, we built a vehicle with 3 possible different configurations. The main thing we changed between them was the propeller size, and we tested 3 wind speeds on each propeller. A limitation was the airspeed measurement in the advanced design wind tunnel. We pulled from a chart and a digital manometer, and we correlated airspeed to that. We were only able to get an accuracy of about plus or minus 1/2 of a meter per second. Also, we made some assumptions in the video grammetry that we used. We assumed that the vehicle moved parallel to the camera and that it rolled without slipping. These are close to being true, but variation could have introduced some uncertainty into our data. We also assumed that the track surface irregularities were small enough so that they didn't cause any significant data. Our final limitation of this project was the wind tunnel track that we made. We would have liked it to be a little longer so that we could have seen some more steady state behavior out of it.
So how do we do the theoretical analysis for right? It's important to know that there are a couple different configurations that you can set a dead downwind faster than the wind vehicle up, right? One configuration consists of setting it up so that the turbine is geared to the wheels in such a way that when the cart is moving slower than the wind speed, that the cart is pushed forward by the turbine. The other configuration is swapping the gears around, so that when it's slower than the wind speed, it's actually being pushed backwards by the propeller. That's how we divide the configurations. So you might say, why would you ever set up the propeller so that it's pushing back on the vehicle? The problem is that when you get to wind speed, the relative direction of the wind velocity on the propeller actually reverses, because you're now, according to the explanation, you're now moving faster than the wind. So the direction of the wind is actually reversed, right? So then the propeller would then be pushing back, and it would be pushing the vehicle forward, right? So we tested the propeller configuration, and the idea is we want to know if the propeller configuration can go faster than the wind from rest. So all of our tests start from rest, and then we drop them in. So how do we do the theoretical analysis for the propeller configuration? We looked at it from an energy point of view, right? So the energy that's going into the system is the wind, right? We're not like we don't have any motors or anything like that in the car. We just set the car down into the wind tunnel, and then the wind just pushes the car, right? So where does the power go from there? Well, one spot that it goes is the drag on the vehicle. That's the only thing actually propelling our car for our configuration because it's the propeller configuration, right? So the propeller is actually going to push backwards on the vehicle. Another spot that power goes is the propeller, right? Something has to spin the propeller, and anything that rotates, it's going to have inertia, right? And it takes some energy to rotate that propeller. The propulsion from the propeller spinning, right? We're assuming that the propeller spinning is actually moving air, right? So there's a propulsive force being created by the propeller, which is in the opposite direction of the car's motion. And then finally, we have the friction force, which we have to overcome.
But now with that in mind, we're going to be looking a little bit at our model design and the construction for the model. So through this project, we ended up having two different iterations pictured here, the first one on the right and the second one on the left. So we're going to get into those a little bit more in the next slide. So the first model iteration, so graduate student Tanesh made this model, and it was constructed, the frame was 3D printed with FDM printing, and it was constructed using aluminum shafts, model aviation wheels, FDM printed gears, and a lot of glue or press fitting to put it together with bearings. So although this did provide an accurate illustration of dead downwind travel with this model, because the gears were 3D printed, there were a lot of inefficiencies with the gears interfacing with each other, since obviously there were plastics, they didn't interface very well. So that's why we decided to make our second iteration of the model, pictured here. So as you can see, a very similar model. The frame was 3D printed, but we are using metal gears. In this, we have carbon fiber shafts, and because of that, we had to use smaller ball bearings. Additionally, we had a collar with set screws, model aviation wheels, and some plastic rods for the frame. So because we used the set screws with the collar to attach the propeller to the model, that allowed us to easily change the configuration of the model by swapping out different size propellers onto it, so we could test how the different size propellers affected the motion in the wind tunnel. So the downsides to this was it's very difficult to change how the gearing works with this model because how it's constructed. A lot of stuff is the bearings are glued in place and the gears. Because of that, we would have liked to do more testing with changing how the gearing is done, but it's very difficult with how this is made. Additionally, as you can see, the model bends slightly forward on the front. That doesn't exactly affect the testing, but it is something that would be nice to be fixed. But overall, we did increase the gearing efficiency a lot by using metal gears, which is what we set out to do with the second iteration. So now for the testing setup. So we used the Advanced Design Wind Tunnel in the Applied Aerodynamics lab at the Kalamazoo Airport. And so what we did is in this wind tunnel, we set up a track. As you can see in the wind tunnel, the bottom of the track is wood, and we have some railings as well as a stopper on the back of the track, so our model doesn't get pushed back into the wind tunnel. And for the setup, we used a high-speed camera with bright lights and a metal rod for holding the model, which we'll see in a later slide in a second. Slide here, we can see some of the testing procedures. So this is sort of a quick version of the testing procedures. We would turn on the wind tunnel, increase the RPM using the wind tunnel control panel there in the bottom left, correlating to 8 meters per second. This is where we had sort of an issue with the resolution because we would have liked, in order to see the speed, we had to use a chart to get the pressure from the wind tunnel and correlate that to a meters per second speed. As you can see, that's the top left image. You can see the gauge there that reads the pressure. And what we would do is place the model on the track onto the marked location and hold the model using this metal rod, which we'll see in a second. while the flow stabilizes, we close the wind tunnel, allow the flow to stabilize, and let the pressure become constant, and then release the model to do our testing. Slide here, we'll see, and we'd set it up, and then when we were ready, we'd start recording, release the model by removing the metal rod, and then when it reaches the bed of the wind tunnel, then it would be out of frame of the camera, and we would stop and then do 3 tests for different speeds for 8, 10, and 12 meters per second for each propeller. Then you can see here, this is when we were doing testing. We have those lights set up directly next to the camera because we used retroreflective tape on the side of the model so that we could use the camera in a program with the frames from the camera in order to detect the light being reflected back at the camera in order to track the motion of the model. And you can see Nate there holding the model still while the velocity is coming up to speed.
Yeah, so now we kind of like to show you exactly what this looks like. Obviously, the video looks very interesting, and that's because we recorded everything in grayscale. So when we play it back, it's very difficult to see things. So we up the contrast a lot, so you can actually see what's going on in the video. But we just want to show you some videos to show you exactly what is the breadth of the speeds that we did testing over. So this is the large propeller, and the wind speed in this is 8 meters per second. And the next video is the small propeller, and it is 12 meters per second. See that it's much faster, but it's not enough to just say it's faster. So I guess we have one more video. This is the slowest versus the fastest. And you can see it's quite substantial difference. So exactly how do we do all of our data processing? Once we had all of our videos and all the images, right? Everything was written in Python, and we used a library called OpenCV to do all the image processing. Basically, what that entailed was we just looked at frame to frame, where was the retroreflective tracker that we placed on the card in the image of the frame, right? So we can pretty easily get a pixel location of where exactly is the center of the tracker, right? So then when we had all that information, we could measure the plane of motion that the card is moving in, right? So the camera obviously wasn't moving, we just set it in one spot. So the cart we assumed is moving just completely parallel in one plane of motion. We just measured the entire width of the area that the cart is moving relative to the image, right? So we basically just got a tape measure, hold it all the way across the image frame where the cart was moving. And then we had a distance about how far is the cart moving when it's from one side of the screen to the other side of the screen. And then from that, we can get a scale to figure out how many meters is 1 pixel or vice versa, right? And then we looked at, again, the position of the tracker in each frame. And then from that, we had the position in actual meters. From that information, we get the velocity and the acceleration or whatever else we wanted, right? But that's not enough. We want to know how much faster is the cart going at a certain set of conditions, right? So to do that, we have to normalize these conditions. So for instance, right, normalizing the vehicle velocity by the wind velocity. If we increase the wind velocity by 1 meters per second, I'm pretty sure that everybody could come to the conclusion that the cart is obviously going to move faster. But how much faster is it moving? Is it moving faster by the same increment of faster? Is it moving 1 meters per second faster? So that we just divide by wind velocity. We also normalize the time by a couple parameters to see a better breakdown of how changing certain physical characteristics about the cart changes our test results. So in the top right, you can see a time constant, which includes the mass and the actuator disk area. That's just the area that the propeller covers, right? So a bigger propeller will have a bigger actuator disk area. And to do that, we normalize the time by those values. So let's show you some of our data. So right here, this is all of these tests were done at the same wind speed, but they're different propeller sizes, right? So you're going to see some pretty common trends, and that's that the smallest propellers move the fastest, and the highest wind velocities have higher normalized velocities. So the cart is actually moving faster on a normalized basis, right? So a couple things to note about this graph. Obviously, the small propeller is fastest, large propeller is slowest, but you can also see that things are on a different time scale. So the normalized time is different, right? This green, the green line doesn't stretch as far, right? And that's because, again, we normalize by time, and the different propellers have different masses in different areas, so they don't stretch as far, right? Another thing to notice is the shape of the graphs here, right? They always go up to some maximum, right? And then they slow down. And that is not because the cart is hitting the side of the track or the cart is hitting the stopper that we have at the end. Those are actually off the screen, right? This is just the propeller. The cart is just moving by itself, just the wind, and it starts to slow down, right? Seemingly, for no reason, right? But obviously there is. This is another example of a constant wind speed when you vary the propellers, right? So again, you see the same trends. You have the small propeller at the top, then the medium propeller in the middle, and the large propeller again at the bottom. If you want to go next. And then this is again for 12 meters per second. And again, you see exactly identical trends in all of these data. Something that you may have not paid attention to, though, is the actual normalized velocity, the magnitude of the normalized velocity is changing between all of those plots. So if you want to go to the next one. Here, this is one propeller, but we've varied the wind speed now. So you can see the effect of what does varying the wind speed actually do. And this is going to be very, similar to the small propeller. The highest wind speeds are always going to be at the top of the next couple graphs, right? So again, you see 12 meters per second at the top. So what does that imply? It implies that if you have a higher wind speed, you have a higher normalized velocity, right? You want to go to the next one? So this is for the medium propeller. It's very, all these trends, you see the same trends in all of these graphs, which is very affirming of how the theory works. And then finally, this is the small propeller. So what is the conclusion of all this, right? The data seems to suggest that the carts are always going to reach some maximum velocity, so maximum normalized velocity. And then the normalized velocity will always decrease. Harvard thinks this is because of the transient effects of the propeller, right? So the propeller is, again, resisting the motion of the cart, right? So we think that there's a transient time where the cart it moves faster, but then as it moves faster, the propulsive effect of the propeller becomes greater, which slows the cart down, right? And it basically stops the cart from ever reaching a normalized velocity of 1, which would be it going as fast as wind dead downwind. So if you can't go as fast as wind, you're clearly not going to be going faster than wind. Another thing is you might wonder, well, if we have all this information, then at the beginning of this we talked about how people will show carts going faster than the wind. For instance, the Veritasium video of a cart on the salt flats going faster than the wind. How is that possible, right? It's likely that because of the uncontrolled conditions of the salt flats, that he can't control exactly what direction the wind is impingent on the propeller, right? So you can't say if you're actually going dead downwind faster than the wind because you don't know what direction the wind is actually coming from. And like we talked about with sailing, if the wind is coming in from an angle, you can in fact go faster than the wind, but not directly in the direction dead down of the wind, right? Another thing is wind gusts. There's no way of actually controlling to have you at a constant speed. So if you have some massive wind gust, and then suddenly the wind dies down, it's going to seem like you're going faster than the wind because the wind speed just dramatically decreased.
All right, so some future developments for this project. If we want to investigate this further, one thing we could do is we could take a regression of the ordinary differential equation from our theoretical model, and that could help us validate it. We could also do further testing in a turbine configuration, which is opposite from what we looked at in this project, which it means that the oncoming wind in a slower than wind regime would actually contribute to the vehicle going faster. Additionally, to isolate drag effects, we could look at a purely drag configuration vehicle, which would have no driven wheels, so the propeller is completely decoupled from the wheels. Additionally, a sail configuration taking a piece of fabric the same size as the propeller investigated and looking at the drag effects. Right, and so the impact on engineering of this project. So greater understanding of dead downwind faster than the wind travel allows for higher efficiency wind power and, of course, different vehicles powered by different kinds of sailboats and such. finally, some acknowledgements. We would not have been able to do this project without the help of Dr. Liu and his grad students, Tanesh and David. So thank you.
Any questions?
Yeah. This is, I'm having a little difficulty. Somebody asking me, I'm an engineer. I will predict the opposite. You know what I mean? Small, lower velocity.
Yeah.
What I mean. So could you explain that?
Yeah, so that's because this is the propeller configuration. So the strength of the propeller is dictated by the size of the actuator disc, right? So if you have a larger propeller, you're going to have a larger actuator disc size area, right? So it makes sense that if you had a larger propeller, that it would be more powerful, right? Yeah. So because it's in the propeller configuration, though, when it's moving slower than the wind, the propeller is actually resisting the motion of the car. It's moving air in the opposite direction that you would think it does, right? And the reason that it's set up like that is because once it's going faster than the wind, the relative direction of the wind velocity actually reverses, right? Because you're going faster than the wind. So then in that regime, going faster than the wind, you would have a propulsive force actually pushing the car forward, right? But the idea is that if you set up your car like that and you start from rest, you're never going to get to wind speed because the propeller is actually, the larger the propeller you have, it's going to push you back further, right? So you're never going to actually get a chance to go faster.
Question?
Actually, there were two theories because in original this image and it explains this vehicle is not extract wing energy driving the vehicles. So in opposite, they think this is a propeller driving. But what is the power to driving the propeller? That's a question. But there originally the people in the YouTube explain because the wind push the vehicle a little bit, so move a little bit, right? So the wheel is connected to propeller. So propeller driving is power is come from the wheel. But the wheel power is come from the wind, drag pushing. So right now this group design trying to check that explanation.
You have some theory?
Huh? Yeah, we predicted. We predicted we can predict roughly correct based on that equations here. Yeah, we model all those equations. But I think our model a little bit too simple. I think their experiment data is correct. It will go up, down. But our prediction so far, the model, it just increase and the sympathetic approach, but it's not go down. So we need to refine the model. But at least these experiments show the vehicle cannot reach the wind speed, right? Much slower than that. Also, larger propeller is not good. Reason is propeller itself acting as energy sink, sucks the energy. So larger, then you absorbs more energy. Therefore, your vehicle goes slowly. So that's basically this experiment proved that. And another design is not propeller, it's a wind turbine. So therefore, gearbox will be set different. That means this wind turbine extracts wind energy driving the vehicle. I think this is a natural way to do it. Yeah, I think your question probably at the beginning you think is puzzling because you more think about the wind turbine. Yeah, that's another vehicle. So later we want to test it. Yeah.
Push and motion is very similar.
Similar.
Turbine actually. Like just I can't see my mouse, but the PI term, the negative PI term is the inertia of the propeller. That just goes away because the turbine is extracting energy. It's being driven by the wind. And then the propulsive term would be a turbine term. You know, have the efficiency of the turbine.
Okay, any other questions? Thank you.